MBA633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. We continue now with our discussion of probability, and in this clip we will discuss the topic of probability distributions. Uh, in short, a probability distribution is nothing but the pattern of uncertainty exhibited by a random variable. So let me repeat that. A probability distribution is simply the pattern of uncertainty exhibited by a random variable. So let's elaborate on that. We go back to our previous tutorials that we had, where we defined the terms experiment, sample space, and so forth. Um, and you remember, a random variable was just a compact and simple way of labeling the outcomes of an experiment using numbers, so that we don't have to write narratives out in long form describing what these outcomes are. Instead, we use the random variable label as a shorthand notation. Now, since there are two different types of sample spaces, namely discrete and continuous, it follows that there are two different types of probability distributions, namely discrete probability distributions and continuous probability distributions. Now, we will keep our discussion of continuous probability distributions for another day. For this clip, we will concentrate only on discrete probability distributions. So let's look at an experiment that we had used earlier in one of our earlier clips. So the experiment consists of the following. I walk up to a person at random and ask them which day of the week they were born. And so this experiment has 7 possible outcomes. So the sample space consists of 7 possible outcomes, the 7 days of the week. And you had seen we had created a random variable called x, and we used the labels 1 through 7 to represent the 7 days of the week. So if we think of these 7 outcomes, and I want to represent the pattern of uncertainty. In other words, what is the probability of x equal to 1, a person reporting the date, their birthday is Monday? What is the probability of x equal to 2, and so forth? What is the probability of x equal to 7? In other words, what is the pattern of uncertainty of this random variable? So to do that, I represent it graphically. For example, I would have a graph with the x-axis representing, showing the random variable with numbers 1 through 7. Those are the 7 days of the week. So and then I would have a spike at each of these points representing the probability of each of these outcomes, and usually the probability is represented by p of x or f of x. Now, how high should each spike be? If I were not if I don't have any prior information, I might start with the argument that, hey, it's equally likely for a baby to be born on any one of the 7 days of the week. If that's the case, I think you would agree that I would draw each of these 7 spikes at the same height, and the height would be 1/7. Why 1/7? Because the sample space has 7 possible outcomes, and all outcomes are equally likely. So the probability of each outcome is 1 divided by 7. So this pattern of probabilities that you're seeing, specifically in this case, this is a uniform. Why? The spikes are of the same height. So this would be called a uniform discrete probability distribution. Okay. Now, there are two properties that any discrete probability distribution must obey. One is you can't have negative spikes. Okay, so every spike, in other words, f of xi represents any one outcome in the sample space, must be greater than or equal to 0. Why? Because we measure probability on a scale of 0 to 1 inclusive. So every spike must be non-negative. The other one is equally important. If I add up all the spikes, how do I add up? I add up all the spikes over the sample space for all outcomes in the sample space. This sum must be 1. It must add up to 1. So these two rules must be followed by any discrete probability distribution. Now let's say I want to be a little more sophisticated. I just don't want to make an ill-informed assumption that it's equally likely that a baby could be born on any one of the 7 days. So how do I get better information? Let's say I go to a hospital, nearby hospital, and look at the day of the week on which 10,000 babies were born. So I look at the day of birth of 10,000 babies, and I've just made some numbers up on the right hand side over here. So let's say I looked at the data, and I find that 1,000 babies out of the 10,000 are born on Monday, 2,000 are born on Thursday, 3,000 are born on Thursday, and so forth. So I'm using historical data now. You remember our concept of relative frequency. So with this data, I can say that based on historical data, the likelihood of a baby being born on Monday is 1000 divided by 10,000, which is 0.1. The likelihood of a baby being born on Wednesday is 0.3, 3000 divided by 10,000, and so forth. So now I can draw the same probability distribution. I have X, and there are 7 outcomes, okay, all the way to 7. And now I wouldn't have spikes of the same height. So I would have the same height for 1 and 2, which is 0.1, but for Wednesday, which is X equal to 3, I would have a spike 3 times this height, and so forth. So I would have different spikes of different height. Regardless of having spikes of different heights, even if you add up all the spikes, they must add up to 1. Okay, so this is a non-uniform discrete distribution, probability distribution, and it obeys these two rules also. All right, now let's look at the second experiment that we had seen, discrete experiment. So I pick up the post on any one morning and count how many vehicle accidents are reported in the paper. So you may recall this was an example of a countably infinite type of sample space. So the random variable that represents the outcomes from this experiment is a countably infinite random variable. In other words, you can identify each outcome, but in principle the count could go up to infinity. Okay, so what is the pattern of uncertainty? What would I do? What is one way I could? So in terms of representing the sample space, I have the letter X, which represents the label for the outcomes, and I have these variables: 0 accidents reported, 1 accident reported, 2 reported, 3 reported, 4, 5, all the way up to infinity actually. All right, technically X could go all the way up to infinity, and I want to know how high should each of these spikes be. So what's one way I could do that? Let's say I go back and look at the last 365 days newspapers. So I go online and I pick up the online version of the Washington Post and go back 365 days, and I count on how many days were 0 accidents reported, and I find that 0 accidents were reported on only one of those 365 days. 4 accidents were reported on 100 of those 365 days. 7 accidents were reported on 40 out of those 365 days. Therefore, based on this historical data, I can argue that the probability of X equal to 4, in other words, there being 4 accidents reported in the newspaper, the probability of having X equal to 4 is simply 100 divided by 365, whatever that comes out to be. Okay. Similarly, the probability of X equal to 1 would be 4 divided by 365. So again, we are using the concept of relative frequency to compute the probability. Now what this table is telling us is that on none of the 365 days did the paper report 11 accidents, 12 accidents, 13 accidents or higher. In other words, the historical data is telling us that the probability of 11 accidents or higher on any one day is 0. So how would I draw the spike? So I would, let me pick a different color here. So maybe the first spike is extremely small, the second spike is a little bit higher. Clearly you can see that the tallest spike would be 4. Okay, the spike for number 5 would be 70 divided by 365 and so forth. So you get a bunch of spikes. Okay, so I'm afraid my machine is a little bit slow, so when I draw these spikes sometimes it goes on the blink. You get a whole bunch of spikes, and technically you have spikes going all the way up to infinity. Again, these two relations must hold. Every spike must be non-negative, greater than or equal to 0. Every spike must be greater than or equal to 0. And if you sum them up over all the spikes in the sample space, in this case there should be an infinite number of spikes, the sum of the spikes must be equal to 1. Okay. So here are examples of a discrete probability distribution. The first example that we had with the days of the week, that's an example of a finite a discrete sample space. This one over here is an infinite, countably infinite sample space, but both are examples of discrete probability distributions. Remember, a probability distribution is nothing but a pattern of uncertainty of a random variable. So it's simply telling you, you ran an experiment, the experiment has a certain number of outcomes. What is the pattern of uncertainty of these different outcomes? Okay, and the probability distribution of for any experiment, any random variable representing an experiment, is the foundation for doing all kinds of probability calculations associated with that experiment. And when we do problems in class, you will see why this concept of a probability distribution is so important. Now, certain patterns of uncertainty occur with some regularity in nature or in practice, and we will discuss two of those probability distributions in another video clip. One would be what is called the binomial distribution, and the other one is called the Poisson distribution, and we will have separate video clips on those. But they are both examples of discrete probability distributions. They're not arbitrary in the sense that they occur with some regularity in nature or in the real world. Okay.